As we begin our investigation of rolling objects, let's take a look at a demonstration that shows a race between a solid disk and a hoop released from the same point at the top of an incline. You may remember this demonstration from last year when we were talking about rotational inertia in our physics class. So try to predict which object you think will win the race, and then let's take a look here. All right, so we see very clearly that the solid disk wins the race. So why would that be? Let's take a look here and see if we can relate this to the ideas of energy. So we've been talking about the fact that when an object moves through space and it rotates, such as when something rolls down an incline, it has two forms of kinetic energy that we must take into account. Let's compare those types of energy for the hoop and the solid disk. So here we have a bar graph representing the potential energy and the kinetic energy at the bottom of the incline. So the potential energy at the top of the incline is the yellow bar, and then at the bottom of the incline, the blue and the green bars would have to add up to the total size of the yellow. And so, this makes sense. Some of the energy is in the form of translational kinetic energy, and some is in the form of rotational kinetic energy. But if we look at the solid disk has a lower rotational inertia. And so the amount of energy needed to cause it to rotate is smaller. Therefore, the amount of energy available for translational kinetic energy is larger, and the object will travel faster down the incline. Again, they both start with the same potential energy, but the hoop has a greater rotational inertia. It needs more of its energy for rotation, leaving less for translation, so it goes more slowly down the incline. All right, so here's another race. This involves our same two contestants, but then also a solid sphere. Look up on your formula sheet. What is the formula for a solid sphere? Where does that formula lie in terms of the mr squared and the 1/2 mr squared for the hoop and the solid disk? And where, which of these objects should win the race now? Let's take a look. All right, so the solid ball wins the race because its inertia is only 2/5 mr squared, which is smaller than 1/2 mr squared or just mr squared. So because its inertia is smaller, then the amount of energy available for motion down the incline will be greater. Now this type of rolling actually represents a very special case of something that has both forms of kinetic energy. When something rolls without slipping, there's an extra relationship between V and omega that we've seen before, but does definitely apply in this situation. So think about maybe a wheel just rolling across a horizontal surface. It has translational motion, which we can describe here. We'll go from its center of mass and think about it having a velocity of that center of mass, VCM. But then because it is rotating, it would be rotating like this. Because it is rotating, it will have an omega value. And so if we look at just a couple of points on the rim, the velocity there would be tangent to the wheel, and then it would have a value of r times omega. So that v sub t represents the tangential velocity at those particular points. But if the object rolls without slipping, then the point of contact, this point down here, must actually be momentarily at rest. That's kind of a subtle idea, but it doesn't slip. And so as it comes down to that point and then goes back up, there's a change in direction and it must stop for a split second. And that allows us then to make a connection between the two pictures. It allows us to say that the velocity of the center of mass must actually equal the tangential velocity, because this point down here is moving forward at VCM, but based on its rotation, it's moving backwards at R omega. And so in order for that point to be momentarily at rest, those two values must equal each other. And this is going to be very useful for our calculations. Kind of an interesting idea about an object that is rolling is that when you put these two things together, not only does that bottom point not move instantaneously, but the topmost point actually moves at twice the speed of the middle. Kind of an interesting idea, and we'll take a look at this in just a second as to how we can see this is actually happening. Right, but again, the summary, the key idea from this set of slides here is that when an object rolls without slipping, it's going to have both forms of kinetic energy, but more importantly, or added to this, is that the linear speed and the angular speed have a very specific relationship, and that is that V equals R times omega when an object rolls without slipping. If it slips, then there's no particular relationship, and so you can't make that assumption. But look for that phrase, rolls without slipping, or a situation where there's enough friction to keep things rolling. All right, so back to that idea of the the speed here being twice as big as the speed in the middle, and the speed at the bottom being actually 0. Let's take a look at a picture here. So here's some physics in action. The spokes down here are very clear. That's because they're actually moving more slowly than the spokes up here. Okay, these spokes you can barely see. They're very blurry because they are moving twice as fast as the axle, okay, which is moving much faster than the points down here, and the very contact point is not moving at any particular instant. So pretty cool stuff.